Okay, so we continue with the study of complex numbers. And we saw how we can represent the same number using either complex, or rather rectangular coordinates, polar coordinates, or exponentials, right? So we're going to continue with that. And this is the some of the operations we talked about before using with complex numbers. But we can also represent phasors based on what's called the Euler's identity, a very famous expression that is called Euler's identity or Euler's formula. And it basically says what it states in here, that an exponential to the power j phi can be represented by the sum of a cosine and an imaginary sine wave, or imaginary sine part. And in this expression, of course, E is just the number 2.7182 that you're familiar with. But it's used for different applications. And one of the applications we're going to use is applying it to the case of phasors. And you may have seen this. Again, this is a famous expression. You may have seen this in posters or T-shirts or whatever. But in the way you get this, or also some people express it like this. Okay. And so it's simple, right? Because all you have to do is, if you take pi as phi, the angle here, right? So if we substitute e to the j pi, then cosine pi is -1. And psi pi is 0, and that's how you get this, right? So, and that's how you get this. If you bring the -1 over this side, it becomes 0. So you may have already seen that before. That's one of the popular ways of looking at Euler's expression. So from this, we can represent a sinusoid as the real component of a vector in the complex plane. The length of that vector is the amplitude of the sinusoid, and the vector v in polar form forms an angle phi with respect to the positive real axis. Another way of looking at the representation of phasor vector is looking at this expression, as the at this point moves along the unit circle. If you kind of look at it coming from out of the screen, you'll see a waveform forming, like I showed you before in the time domain, right? Other than, and this one is at this angle. But you can follow, see, as many circles as you have in here. You have 3 circles. Each one is following a trajectory, and this one can show that trajectory in the time domain, right? So what that means is that the phasor is spinning around the complex plane as a function of time, right? So it's just a way of representing the same expression as in this plane, the unit circle plane, or in the time domain plane. And as a way also adding phasors of the same frequency, a very easy way. So again, Euler's formula is this. The real part of this exponential gives you the cosine of the angle. The imaginary side of the exponential gives you the sine of the angle. So we can represent a voltage V of t, a sinusoid like this, right, with Vm cosine omega t plus phi. It can be represented, since it's only the cosine, it can be represented by the real part of this expression, see? So if we take the real part of this expression and we expand it using Euler's formula, we get exactly the same V of t. So another way of representing these expressions is by looking at using an Euler's formula in terms of the real part. Now, this expression here, right, if you look at this exponent, Wt, omega t plus phi, is the same as multiplying 2 exponents of two functions of these exponents, right? So this addition is the same as this product, right? So we can expand this as the product of two exponents. And if we do it that way, you'll see that by taking the this expression, Vm e to the j phi is the actual phasor, right? Notice here, it's just the phasor representation, right? So another way of representing this function of time is by saying, if we take the real part of the product of the phasor times the exponent e to the j omega t, we get the same function again, because this v, we use light phase, italic letters by the way, to represent functions of time, but we're gonna use bold phase letters like this to represent phasors. Okay, so anytime you see that in your book or in any literature, capital boldface will typically mean a phasor quantity. So in this case, this phasor is written, can be written as an exponential, right, associated with the same amplitude, or as a phasor, right? Because remember, this exponential is tracing the signal at this angle. So this represents the same thing. This is another picture showing the relationship between, you know, the exponential in time and what it does in the different planes, right? So if you were to take that unit circle outside the plane, going out of the, you know, the plane, you'll see what is called a helix effect, right? Going out, and that represents this this expression, where the exponential is part of two components: a real component that is the cosine, right, along the x-axis, and an imaginary component that forms the sine wave along the y-axis. See, and that's what will form that helix effect that you'll see here, coming out of the plane. Now that's not important for us. It's just a little graphical representation to show you how that relates, okay? What's important to us is to understand that we can represent phasors by using rectangular coordinates, polar coordinates, or exponentials like this. So phasors are typically represented at time equal to 0. And if we do that, then the representation or the transformation between time domain to phasor domain is really simple. So if we look at a signal in the time domain, where this is the representation, the time domain representation, then in the phasor domain is represented just by the amplitude and the angle, where it's clear that we are representing this voltage in one of two ways or in both ways, right? This way represents the same voltage. This way represents the same voltage. It's just different ways of representing the same quantity. And one way here, for example, we're looking at it in the time domain, where the function of t, voltage, is just the real part of that phasor times the exponential e j omega t. And in this way, again, we're representing that phasor, right, that is moving counterclockwise in this direction at a frequency omega radians per second, and is making an angle phi. Okay. So again, that's the same, you know, same representation of the two of the signal in two forms. Again, when we move counterclockwise, we're saying that this is the leading direction. And when we move clockwise, we're saying that this is the lagging direction, right? So in this picture, this phasor here, V, is equal to this amplitude V at an angle of phi. And this phasor I is equal to this amplitude IM at an angle minus phi. Minus phi because it's, you know, in the other direction. Of course, by trigonometry, you know that this angle here is the complement of the angle that goes all the way around up to this point, right? So, you know, it's all relative of what direction you're showing. But in general, if it's moving in the counterclockwise direction, remember, it's leading. And if it's moving in the clockwise direction, it's lagging. All right, another representation of phasors in the time domain and the frequency domain. And I'm sorry, in the phasor domain. Well, phasor, you'll see later that we can also refer to the phasor representation as the frequency representation. It's another way of calling it. But in any case, what you can see here is that this case here, right? If you're standing here, right? If you're standing at this point in the horizontal axis, and these two signals are moving, these two arrows are moving counterclockwise, right? As they start moving counterclockwise again, the first one you'll see is the blue one, right? You'll see the blue one, and as they are right now, right? As you're standing here in this horizontal plane, the first one you'll see is the blue, and then as time passes by, eventually you'll see the red, right? So that's how you can determine who's leading who in the phasor domain, and this is how you can determine who's leading who in the time domain, because this is again happening first, right? The blue one is happening before the red one. So this is a summary of how we can transform between time domain and phasor domain, right? Again, this is the representations we have been looking at. Our point of reference is always going to be cosine waves. So if we have to represent a sine wave, we're going to have to include a -90° here. Same thing for currents, right? So it's normally that we use cosine waves to represent all the signals. If we use sine waves, we have to include this -90° factor in the representation. So notice also that the frequency of the phasor is not explicitly shown in the phasor representation, right? It's not, right? In the time domain representation, we see it, but in the phasor domain representation, there's no information about the frequency. But the phasor domain is also known as the frequency domain representation. And it yields some important, interesting results. If, for example, we're looking at the derivative of a function, if we apply phasors to this function, it becomes a product, see? So, and you see how that has very interesting applications a little later. But in the time domain, representing this expression as phasors becomes the product of j omega times the function b. If we integrate in the time domain, in the frequency or phasor domain, we simply divide by j omega. So in other words, multiplication in the frequency domain by j omega is the same as derivation in the time domain. And division by j omega in the frequency domain or phasor domain is the same as integration in the time domain. And you'll see how this is applied. The very important part of this, if you can imagine, is that remember if you study, when you study capacitors and inductors in DC, and you started analyzing circuits, RLC component circuits, if you remember, for every LC, for every L or C that you have in the circuit, you added a degree to a differential equation, right? So in other words, when you analyze a circuit using any of the techniques in the time domain that includes an inductor or capacitor, you end up with differential equations. Okay? And as you notice, as you see later, the beauty of this is that those differential equations, when we move in the phasor domain, become algebraic equations, right? Because there's no longer any derivative here. There's no longer any integration here, right? So keep that in mind, even if it's not that clear for now. So again, this is what I just mentioned just now. Differentiating a sinusoid is equivalent to multiplying the phasor by j omega. Integrating a sinusoid is equivalent to dividing the phasor by j omega. So the difference between VOT, or the time domain representation of the voltage in this case, could be current, and the phasor should be emphasized. VOT again is the instantaneous or time domain representation, while V boldface V is the frequency or the phasor domain representation of the same signal. V of t, of course, is time dependent, while V phasor is not. Okay, V phasor is not time dependent. V of t is. V of t is always real. There's no complex terms. Well, in the complex representation or in the phasor representation, V is generally complex. Okay, I know that's kind of difficult to visualize sometimes, but remember those rules, or remember those points about time domain representation and phasor domain representation, okay? So let's look at some ways we can evaluate complex numbers. Let's look at an example here. We have 40 at an angle of 50 plus 20 at an angle of minus 30, and we're raising that to the 1/2, or in other words, we're taking the square root of that quantity, right? So one way we can do this is by first using polar to rectangular transformation. It might be easier to do it that way. Because we can't add directly these quantities as they are, okay? There's no way we can just add them like that. So we're gonna need to put them in rectangular coordinates. So easy, right? To put this in rectangular coordinates, we simply transform. Remember, this represents, if you graphically look at this, it's just it's just 40. If this is an angle, so more or less angle of 50, right? And is in this direction, and this is 40, right? And this will be I don't know, something like minus 30 because it's in this direction, and the amplitude is 20. So that's what we want. That's what we added, right? We adding those two phasors, right? That's what we're doing here. So what we're going to do is we're going to look at the components, right? Like the components of this 40 angle. I mean 40 amplitude and angle of 50. Sorry about that wiggly line, but right, we have a 50-degree angle, and what we want to know is the component along the y-axis and the component along the x-axis, so that we can find that point in rectangular form. So if you look at it that way, then the 50 degrees, the x component is cosine of 50, and the y component, because in that direction is the imaginary axis, is sine of 50. Okay, and that's how we get those numbers. So it's 40 times this component in the x direction, and it's 40 times this component in the y direction, and that gives us this number. Same thing here, right? If we apply the same rule, it'll be cosine of minus 30 for the real part, sine of minus 30 for the imaginary part, multiplied times 20 gives us this. And now we can add them together. So now we can add real with real and imaginary with imaginary to get this. Now that we have it in that form, it's easier for us to go back to polar coordinates. Because in polar coordinates, we can apply this simpler rule here to find the square root of that number, right? The square root of this number. So, so again, we have the expression in rectangular coordinates. We can simply put this in polar coordinates, right? We simply just add the square of this number plus the square of that number, take the square root, and you get that. And they take the arctangent of the imaginary part over the real part, and you get this number, or this angle. Okay? And so now all we got to do at this point, this is the result of adding this two. So the last thing we need to do is take the square root. But now we have an polar coordinates. To take the square root, we simply take the square root of this number, and we get 6.91, and we take half of this angle, which is give us 12.81, and that's the answer. All right. All right, so now let me just continue with this. Now we're going to look at this complex numbers, and we're going to